I'm going to start off with equilibria. So I'm going to start off with equilibria. It's quite a longish topic, so what we might do is spread it over the 2 sessions, and we'll see how far we get, because there's sort of 3 sections to it. So what we're going to do first of all with equilibria is we're going to look at what dynamic equilibria are, understand what the equilibrium constant is, and then be able to calculate the equilibria constant. So equilibria is all to do with reversible reactions. So if a reversible reaction is carried out, and this is a really important part, is if we carry out in a closed container so that none of our reactants and none of our products can escape, we can reach something that we call a dynamic equilibrium, and that's a state that we can establish. But it is really important that we remember it has to be in this closed container, so none of our reactants or products can escape. And if we reach a state of dynamic equilibrium, we have this. So A and B, whatever our products are, make C and D, but also C and D can make A and B. So this state is dynamic because both the forward and the reverse reactions are going on. So we actually get to this point of dynamic equilibrium where both are happening at the same time. It is in equilibrium because the rates of the forward reactions and reverse reactions are exactly the same. The net concentrations of the components of a reaction mixture remain constant. And my screen had it. Oops. That's really annoying. And so they remain constant. So that is what equilibria is. So we have A plus B going to C plus D, but it can also reverse back. And the dynamic equilibria is when it can be happening at the same time. So what happens if our equilibrium lies to the right? So some reactions produce a very, very high equilibrium yield of product. So we get lots and lots of product being produced. So a large percentage of the reactants react to form products. So we say that the equilibrium lies to the right. And so it doesn't necessarily, because of equilibrium, just because we're making the same amount both ways, doesn't necessarily mean that we get the same yield both ways. So this way, if our equilibrium lies to the right, we're going to have a higher equilibrium yield of products. So you can see from this graph, over time, our concentration of products increases and our concentration of reactants decreases when it reaches that point of equilibria. We can have our equilibria lying to the left, which is the exact opposite. So some reactions produce a very low equilibrium yield of product. A very small percentage of reactants actually react to form products. So we say that the equilibrium lies to the left. So in this instance, we've got all the reactants up here, and we've got all the products down here. And the products, there is an increase in products, but it's nowhere near as high as the amount of reactants. So that's why we'd say it would lie to the left. Then we get something called the equilibrium constant. So we've basically looked at what equilibrium is, how it works, and then now we've got the equilibrium constant. So at equilibrium, what happens is we have a ratio of concentrations of products to reactants is constant. So that ratio shouldn't be changing once we've hit equilibrium. It doesn't mean that they're exactly the same ratio, but it means that the ratio is constant. It doesn't change. So the ratio value is called the equilibrium constant, and you often see it as Kc. And it is always the same for a particular reaction under fixed conditions. Obviously, if you change them conditions, even ever so slightly, that value will change, but otherwise the equilibrium constant is always the same for particular reactions. So for the general reaction, A plus B goes C plus D, this is how we would work out our equilibrium constant. We would have C, and then to the power of C if there was any powers there, D to the power of D, and we would divide them by B to the power of B and A to the power of A if there's any powers there. So again, I'm going to use some actual numbers in a moment to actually demonstrate this to you. That's a really important equation to make sure that you've got written down at some point, and make sure you really know it, because you get asked this a lot. You get asked to calculate equilibria, equilibrium constant, and you won't be given the equation at all. So it's really important that you know it and you are happy with it. So again, the little c's are saying that they're the power. So if there was any multiples, and it will make more sense in a second. So we're going to look at units for calculating equilibrium constant, because they're a little bit strange. They are a little bit strange, and I'm going to sort of do some example questions and sort of show you the answers that we typically expect students to come up with, and they're not always necessarily right. So our units of equilibrium constant actually vary. And so we calculate them from the equilibrium constant equation. So for example, if A plus 2B gave us C plus D, we would need to find the units of equilibrium constant. So we would write down our expression for the equilibrium constant again. So Kc equals, and this time we know if we have any extras, we know if we've got any of those 2 lots of A or 2 lots of B. So here, straight away, we know that we are, let me go on here and draw a pen. We know, I've lost my pen, that we've got 2 lots of B, for example. So we know we've got 2 lots of B. So we can fill this in straight away, and it's okay, well, we put our products at the top. So CD divided by A to B to the power of 2 for B, because we've got 2 lots of B here. Then what we do is we then go in and we insert the units into the equations. So moles per decimeter cubed is our units that we will use. So top is just moles per decimeter cubed for both. Bottom, moles per decimeter cubed, moles per decimeter cubed to the power of 2 at the bottom. This is where it gets interesting. So we then cancel out our units that appear on both the top and the bottom of the equation. So obviously, nothing's on the top because we can cancel them out, the top and the bottom, and actually we can cancel this one out because we've got this one occurring twice, so we can cancel it out. So we just have 1 lot here. So it's 1 over the power, 1 over moles per decimeter cubed. Therefore, all unit terms must be on the top half of the fraction, so the sign of the power on each unit is changed. Therefore, we have power of -1 and decimeter cubed here, so it's moles -1 decimeter cubed, and that is really important. So we cancel out units that appear on both the top and the bottom of our equation. And then D is the important bit that people miss out, is all unit terms must be on the top half of our fraction. So because of that, we need to reverse our equation. So the sign of the power on each unit is changed, because obviously that was positive there. We're going to reverse it, so then it becomes negative, and that becomes positive. So what are the units of Kc, so our equilibrium constant, for the following reaction? Well, if we drew this out, oh, is it not going to let me draw on here? Right, let me get this up. I'll draw it like this then. Here we go. So if we drew this out, we would have NO2. Top got 2 lots of NO2. Got N2O4 on the bottom. Well, if we put our units back in, we've got moles dm -3 twice, and moles dm -3. So we can cross that one off. We can cross that off, but actually just cross it down to a 1. So we just have that 1 remaining. So it should be moles decimeter -cube. Why it's nothing working. that's on question 5. I want it to be on question 4. One second, sorry about this. Okay, here we go. We'll have a look at this again. Annotate, let's clear the screen, clear all drawings. And go back to mouse. Okay, so I can work out how to make this bigger again, and will. No, not a clue. Here we go. So, sorry about that. Let's go back to multiple choice quiz. Let's put our annotations on again, and let's have a look at this. So, which is the Casey expression for the following reaction? Okay, well, we know we go with A plus B equals, well, C plus D, but we obviously don't have D in this situation. So we're obviously going to want, our products always go on the top. So C is going to go here. A and B are going to be at the bottom. Now we've got 2 lots of A. We're going to put A to the power of 2. That should be the top one there. Should be our answer. So there, let's move on to the next one. Let's erase everything off here, clear all drawings. Okay, so what is the Casey expression for the following reaction? So if we have a look at this one, we've got N2 plus 3H2 to 2NH3. So products again, right-hand side always is on the top. We're not going to want to break things down. We don't want to put, this is just wrong because we haven't got 2 lots of nitrogen and 2 lots of hydrogen. We don't break it down on that. So we're just going to go straight away. No, it's not that one. We have got NH3. Yeah, NH3, but we've got 2 lots of NH3. So we know it's going to be this one, but let's just double check the rest of it. Got N2, N2, H2, H2, H2 3 times. Yeah. So it's going to be that. Okay, what are the units of Kc for following reaction? So again, we can do the cancelling out situation. So we would have mole on the top. Let's draw it out on the bottom. We've got A here. And then we've got B here. And that's power 2. Or we can cross the top out and we can cross one lot of them out. So we've got both of them here. So it would become moles minus 2. We've got 2 lots of moles, but obviously we're moving the top to the bottom. So we have to reverse the operation. So it's moles power minus 2, deciliters power 6. We've got our minus 3 here, minus 3 here, reverse our reaction. So it should be 6. Reverse our operations, even not reactions. So mole minus 2 power 6. There we go. And then number 4, because I've already done number 5 randomly. What are the units of Kc for following reaction? So really quick way of doing this one, we just have a quick look and we go, okay, how many moles of this have we got? Well, we've got 1 mole here, got 1 mole here, got 1 mole here, 1 mole here. If we put them all out, here, I'm just going to do this really quickly, like this. I know it should say mole. I'll do that really quickly here. Mole, good. Mole, good. Cancel them out. Okay, well, this can cancel with this one can cancel with this one. Oh, hang on, there's no units. That is correct, there is no units. Do not panic if you get anywhere you think it's no units. So what we're going to do now is just going to clear all these drawings so we can actually see what we're looking at, is we're going to have a look at some calculations. Now, this whole calculation is based on this question here. So the question is, if we have got 1.5 moles of CH4 and we have got 3 moles of water and we heat it in a 100 cubic centimeter vessel, we get at equilibrium, we get 0.2. So at equilibrium, we get 0.25 moles of CO2 formed. And we've got the equation. Let's scroll down so you can see it. CH4, which is our gas, plus 2H2O goes to CO2 plus 4H2. So what we're going to do is going to work out the equilibrium constant. This. So step 1, we are going to work out the number of moles of each species at equilibrium. And we're going to use our ratio of reacting species to work out how many moles have reacted. So we look at this and we go, okay, we've got here, our ratios are going to be 1 to 2 to 1 to 4. We've been told at the beginning of that how many moles we started off at the beginning of the reaction. So at the beginning of the reaction, we were told we started off with 1.5 moles of CH4, and we started off with 3 moles of water. We know we produce at equilibrium 0.25 moles of CO2 here. Okay, so this is where we need to work out how many moles have reacted. Well, we know it's 1 to 2 to 1 to 4. So moles at the start is 1.5 to 3, and that is our ratio of 1 to 2. And you can see that's clearly 1 to 2. 2 lots of 1.5 will give us 3. At the end, we know it's a ratio of 1 to 4, and we know at equilibria we have 0.25 moles of carbon dioxide. So if it's a ratio of 1 to 4, that means that we must have 1 mole of 4H2, which means we've got 1.25 moles on this side in total. So to have got that, we have certain amounts of moles that must have reacted to have got that far. So our number of moles at equilibrium, this part, well, we've had 0.25 moles reacting here. And so we're now at 1.25 because we've decreased, and we've had 0.5 moles reacting here. So we've gone down to 2.5 moles at equilibrium, and that is our ratio. And again, we can see that it's still fitting our ratio of 1 to 2. So step 2, what do we do now with this information? Well, we work out the concentration of each species from the number of moles calculated in step 1. So to work out our concentration, we do number of moles, which worked out in step 1, divided by our volume. And we knew our volume was 100 cubic centimeters. In decimeters, that is 100 divided by 1,000, 0.1. So to do this, if we walk it through here, I know it's giving you roughly here. If we walk it through here, we go, okay, moles at equilibria, CH4, we've got 1.25 moles. We're going to divide it by its volume, and we should get 12.5. So our volume would be 15.625. And so that is how we're going to work out our concentration of A, because we have our moles of A divided by our volume of the substances. Then what we're going to do is, if I can use my mouse, step 3, we're going to write down our expression for Kc. So again, we know that it's going to be products on the top. So we have CO2 and our H2 at the top, CH4, H2O, 2. Then step 4, our final step, we're then going to insert our values into the expressions. So the values that we are inserting here is our concentration, not our moles. So it's really important we're inserting our concentration values here at this point. So 2.5 times 10 to the power of 4 divided by 12.5 times 25 to the power of 2. And that will give us 3.2 moles. I'm going to go through the units with you now and how we get these units. So if we have a quick look at units again, we've got CH4, so that'll just be moles. And we've got, oh no, sorry, CO2, and then we've got H2 so that would be moles to the power of 4. Divide this by our CH4 and our water. And our water is to the power of 2. Yeah. So let's do some cancelling out. Okay, this can cancel out this. We've got 2 here that can cancel out 2 of them. So we've got 2 of these left. Well, okay, the positive, so we don't need to do anything to that. So that'll just be moles to the power of 2, 6. And so that's how we've got those units, 3.2 moles to the power of 2, moles squared, decimals to the power of -6. So mouse. Clear. Quite. Why is this working? Okay, so we're going to look now at the value of the equilibrium constant. So the size of the equilibrium constant tells us how the equilibrium mixture is made up. So it's basically our products divided by our reactants. So if Kc is greater than 1, the concentration of the products is greater than our concentration of our reactants, and therefore we say that the equilibrium lies to the right-hand side. Vice versa, as you can probably imagine, if our equilibrium constant is smaller than 1, then the concentration of reactants is greater than the concentration of products, and therefore we say that the equilibrium lies to the left-hand side. So here are some examples of some questions. What I want you to do is pause when you watch this back later and have a go. And what I'm going to do is I'm going to talk it through what you would do, but I'm also going to show you some of the questions that other people would, answers that other people would come up with, because there's a reason why they've given this whole range of answers on here, and you'll see that quite well. So basically, let's just set up our Kc equation. So we would have this, we'd have NO up here, O2 here, and we would have NO2 to the power 2 here. Okay, so straight away we can look at this and we know that our units are going to be, if it asked us for units, obviously it's not, but our units would be moles. There we go, because this will cancel out, this will cancel out, and we're just left with that. So let's actually have a look at inputting some of this information then. So we've got 0.56 moles of NO2. So we've got 0.56 moles of NO2. And we need to find the concentration. So we're going to get 1.12. But we're going to do 1.12 power of 2. And we're also going to have, what have we got? Oh no, that's not NO2. This is me not reading properly. Well, we do have that, but that will be on the bottom. Sorry, so that'd be 1.12 2 here. How many moles are formed? Okay, so it's 2 to 2 to 1. So we've got 0.48 moles of NO formed. So that's 2 to that. So we'll divide that by 2. So we've got 0.48 moles of 2NO, and this we've got 0.24 moles. Okay. Again, we need the concentrations. Should have 0.96. And 0.96 to the power of 2. I'm going to pop all that through. Why is the mouse not working? No, here we go. I'm just going to pop this all into my calculator because I foolishly decided not to work this out before doing this. So I'm just putting in that equation there into my calculator, 0.48, 1.2. Why is nothing clicking on the right buttons? Just having a bit of a moment because nothing is clicking on the right buttons. Oh, that's not what I wanted to do. Oh, right, that's a different question though now. Just give me. Right. So I just wanted to get this up to talk it through with you because it's just a bit easier than my crazy ramblings. So basically what we want to do is we want to calculate the concentrations of each species at equilibrium. So we have 1 mole of oxygen, like I was saying, is produced for every 2 moles of NO. So at equilibrium, we know there must be 0.24 moles of oxygen, which was my crazy ramblings earlier. Therefore, we have 0.48 moles of NO2, and that has been used to produce 0.48 moles NO. So 0.56 minus 0.48 equals 0.08 moles. Therefore, we're then going to calculate our concentration of each species at equilibrium. We're going to do concentration, and that will equal moles divided by volume. We know our volume is 0.5. So NO2, as we've said here, is 0.08 moles. We're going to divide that by 0.5, and so we get 0.16 moles decimal cubed. NO, we have 0.48 divided by 0.5, and that'll be 0.96 is our concentration, and then 0.24 divided by 0.5, and that should give us 0.48, which is what I was showing you we've got. Then we write this whole thing out again. So we write the expression for Kc, find Kc by substituting our values. So we should have 0.96 squared by 0.48. My calculator decided to do something naughty there. And then divided by 0.16 squared, and that'll give us 17.28 moles. So let's have a look at the Next one. So we've got 2 moles of ethanol, and we add that to 2 moles of ethanoic acid. So 2 to 2. At equilibrium, there are 0.67 moles of ethanoic acid. And so we need to find the value of the equilibrium constant. Well, if we look at our ratios again, we've got 1 to 1, 1 to 1. So if we've got 0.67 moles of ethanoic acid here, we have 0.67 moles of water. So let's have a quick look. I want it to come up something. No, I know that. Just want to come up the answer. Here we go. So what we need to do is we need to calculate our concentrations. So 1.33 moles of ethanoic acid have reacted, and we know it's 1.33 moles because we had 2 moles at the beginning and 0.76 moles. We've now got product of 0.67 moles, so we need to take that off our 1.33. And 1.33 moles of ethanol must have reacted to leaving 0.67 moles at equilibrium. Therefore, 1.33 moles of ethyl ethanoate and water together were formed. If you're wondering where the 1.33 moles have come from, what we've done there is we have done 0.67 moles twice, and that will give us our 1.33. So then we're going to write in our expressions for the equilibrium constant again. So we've got our ethyl ethanoate and our water on the top, divided by our ethanoic acid and our ethanol. I'm going to put in our values. So we've got, oh, my mouse isn't working, 1.33 moles, 1.33 moles, 0.67 moles, 0.67 moles, divide them all together, we get 3.94. And if we were looking for a unit, there would be no units because they would all cancel each other out. And then the final one, so we've got 1.58 moles of N2 and 4.74 moles of hydrogen. And we heat these in a 0.75 decimeter vessel. At equilibrium, 2 moles were present. What is the value of Kc? Okay, so we've got 2 moles of NH3, but we've got a ratio here of 1 to 1. Why is that 2 at the top? No. Like 2 at the top's confusing. 2 should be at the bottom. 1 to 3 to 2. Okay. So let's double check our ratio. So we've got 1.58 moles of N2 times that by 3. That means we have got 4.74 moles. Okay. We can work out our concentrations of that. So we can do 1.58, divide it by 0.75, and that equals 2.106. But we want to have, so this is how much is present. NH3 was present at equilibria, so there will be 4 moles of that present at equilibria. So let's go through the answer. Let's get it up. Yes, I know that's the wrong answer. I want it to be the wrong answer because it won't show the answer otherwise. Here we go. So we're going to calculate the number of moles of each species at equilibrium. So 2 moles of NH3 are formed, and in that case we would have used 1 mole of N2 and 3 moles of H2. So 1.58 minus 1 equals 0.58 moles, and H2, which was 4.74 minus 3 equals 1.74 moles. Then you need to calculate the concentration of each species at equilibrium. So divide all of them by 0.75, which was our volume, and then write our expression for the equilibrium constant. So we'd have NH2 to the power of 2 divided by N2, H2 to the power of 3. And then we'd substitute our values. And obviously this time, we then get a value of 0.74 moles to power minus 2 decimeters to power 6. Why have we got that as our answer? Well, if we have a look about our cancelling out, That 2 will cancel out then, so we've just got that left. So we've got 2 lots of it here, which would be moles decimal cubed times 2. We're going to flip them so they're on the top. So then obviously that becomes -2. That becomes 2 lots of 3 becomes 6 plus 6. Okay, so let's go on to Le Chatelier's principle. So equilibrium constant, we're going to have a look a bit more at this. So we're going to look at what gas equilibria is and what Le Chatelier's principle is. Be able to calculate partial pressure and then be able to calculate equilibrium constant. So for reactions involving gases, it's actually really difficult for us to measure the concentration of a particular gas. So what we do instead is the quantity of each gas in an equilibrium mixture is described in terms of the pressure that it exerts rather than the actual concentration. And this is what we refer to as partial pressure. So to work out partial pressure, which is PA, we have our mole fraction, which is XA, multiplied by our total pressure, which is P top. So the mole fraction, we find this out by mole fraction of A is our number of moles of species A divided by our total number of moles of all the species in the reaction. So it's just a fraction of a moles. That's literally all working out. So we're going to work through calculating partial pressure. And I think we're going to do it of this equation to the right. So our pressure total is 20,265 kilopascals. And our equation is nitrogen plus hydrogen, 3H2, goes to 2NH3. So let's calculate our partial pressure first. So we're going to do our mole fraction, because obviously the equation that we need to do, is it going to let me draw on here again? No, apparently it doesn't want me drawing anymore. The equation that we need to do for partial pressure involves mole fraction. So we need to work out our mole fraction. So in this equation, we've got 1 mole of nitrogen. And how many moles do we have in total? Well, we've got 1 mole of nitrogen, we've got 3 moles of hydrogen, and we've got 2 moles of NH3. So we've got 6 moles in total. So mole fraction would be 1 divided by 6. That is our mole fraction. And then to work out our partial pressure for this, we do 1/6 times by our partial pressure, which is, not partial pressure, sorry, our total pressure, which is 20,265 kilopascals, which would give us the pressure, the partial pressure of nitrogen as 3,377.5 kilopascals. So then we do exactly the same thing, but this time for our hydrogen. So in the equation, we have 3 moles of hydrogen molecules to our total of 6. So mole fraction is 3 divided by 6. So again, we go 3 divided by 6 times 20,265 kilopascals will give us 1,132.5 kilopascals, and that is our partial pressure of hydrogen. Ignore that says water because that is incorrect. And then finally, we want to work out our partial pressure of ammonia. So exactly the same, we've got 2 moles of ammonia, 6 moles in total, 2 divided by 6. So we're going to do 2 divided by 6 times by 20,265 kilopascals, which is our total pressure, and that will equal 6,755 kilopascals. So that is calculating our partial pressures. So gas calculations. At equilibrium, there are 2.5 moles of A, 2.5 moles of B, and 1 mole of C. What you need to do is calculate the mole fraction of A. Okay, that's actually really quite nice. Let's get the draw pen on. You would just add up all your moles. So you would do 2.5 moles, add 2.5 moles, add 1 mole, which obviously is 6 moles. So our mole fraction would be 2.5 divided by 6. which would give us 0.417. There we go. So write down your mole fraction equation, then do your mole fraction. 2.5 divided by 2.5 plus 2.5 plus 1, which is 2.5 divided by 6 equals 0.417. Here we go again, similar thing. At equilibrium, there are 0.25 moles of A, 0.63 moles of B, 1.51 moles of C, and 0.65 moles of D. Calculate the mole fraction of C. So again, whatever it's going to be, where is C? I've lost it. 1.51 moles of C. So let's look at how many moles we have in total. Remember, we've got 2 lots of C. So we're going to do 0.25 plus 0.63 plus 1.51 plus 1.51 plus 0.65. So we should have a total moles of 4.55. 2 lots of 1.51 gives us 3.02. And that will equal 0.664. Oh, have I done that and I've not needed to do that? 0.25 plus 0.63 plus 1.51 plus 0.65. 3.04, 3.04, 1.51 divided by 3.04, 0.96. Right, we didn't need to double C, so I made a silly mistake there, which was my own fault. So what I did was I doubled C as 1.15 because I was like, oh, there's 2 lots of C, but obviously that's odd even ratio. When we're looking at partial pressure of gases, we don't need to take that into account. That was me being a bit silly there. Question 3. So at equilibrium, the mole fractions are SO2 minus 0.46. Are these supposed to be minus numbers or are these just dashes? I'm going with minus numbers. So we've got our mole fraction, 0.46. Our pressure is 100. So it should be 46 kilopascals. Yeah, I'm not quite sure why there was a minus there. I think they were just attributing it to each one, and that just really confused me. So again, to work out partial pressure, it's just our mole fraction multiplied by our total pressure, substitute our known values in, and that would give us 46 kilopascals. Again, at equilibrium, they've given us a mole fractions this time, which is nice, and we've given our total pressure. What is the partial pressure of NH3? Okay, so we've got 0.37. So all you're going to need to do, I'll write this one out. You're going to get 0.37, and you're going to multiply that by 1.65 times 10 to the power of 3. I'm just going to do that on my calculator now really quickly, because I can't do that sort of maths in my head. Oops, I would help if I didn't press one button on my calculator. 0.37 times 1.65 times 10 to the power of 3. 610.5 kilopascals. There we go. And then the last question. So we need to work out our mole fractions. So this one, we need to work out our mole fractions. We've just been given our moles, so we need to work out our mole fractions and then our partial pressures. So we don't actually need to work out mole fractions for all of them. because we're just being asked the partial pressure of PCl5. So we've got 0.67 moles of PCl5. So that's going to go on the top, 0.67 moles of PCl5. We need to add all our other moles up to get our total number of moles. So we've got 0.67 moles plus 0.33 plus 0.33. Which would give us 1.33. So 0.67 divided by 1.33 would give us a mole fraction of 0.504. Now, we just now need to multiply that by our total pressure, which is 250, which gives us the answer of 125.9, which would be our 126 answer. I'll just clear that so you can see that if you want to read this again. So again, we just need to work out a mole fraction of PCl5. We don't need to work out mole fractions for all of them. You can, isn't needed. So we substitute our known values in, write down the partial pressure equation, substitute our known values into the partial pressure equation, and we get 126 kilopascals. I'm going to stop here actually, because I'm not going to go on to the next bit, because then that's